Welcome to Calculus. Whatever confidence you have will be tested. But don't worry, Stevenson has tools to help you. On this episode, Stevenson will demonstrate what is a derivative? Well, the good news is you've kind of already been doing it. So in section 1.4, we define the slope of a curve of y equals f of x at some point where x equals a to be this formula. Look familiar? Well, when it exists, this limit is called the derivative of f at a. So in this section, we will investigate the derivative as a function derived from f by considering the limit at each point on the domain of f. So, what is a derivative? The derivative of a function of f with respect to the variable x is the function f prime, whose value at x is f prime of x equals the limit of f of x plus h minus f of x all over h as h approaches 0, provided the limit exists. The domain of f prime, the set of points in the domain of f for which the limit exists, may be smaller than the domain of f. So in other words, your domain of your derivative could end up being smaller than the domain of your original function of where it comes from. If f prime does exist, we say that f has a derivative or is differentiable at x. A function that is differentiable at every point of its domain is considered a differentiable function. So let's actually apply this definition and see what it means. So the example says differentiate, in other words, find the derivative of f of x if f of x equals x cubed. So by applying the definition, we can see, here it is, f prime of x equals, and here's our limit definition. So f of x, if you remember, so f of x plus h means plug in x plus h, right, into f of x. See the blue writing on the side? The blue writing is super handy. It helps explain some of the steps that you see in the example. So this is x plus h cubed, and then what is f of x? It's just x cubed. Now you're going to expand x plus h, quantity cubed, you get this polynomial, and then here's the minus x cubed. Be very careful of your signs. And as what it says here, they're going to cancel out the x cubed term, so here and here, and take a single h and factor it out. Remember I had mentioned you can do two steps in one and simplify your work. Now the h's will simplify here, and you're left with this limit. It is now safe to take the limit. So we're going to take h and substitute 0 in. It's going to go in right here and right here. And notice we're left with 3x squared. What this means is the derivative of f of x, x cubed, is 3x squared. So if I wanted the slope of this f of x function, any point I want it, all I have to do is plug it into here. So let's say I needed the slope at 1. I could plug 1 into here and I'd figure out it's 3. What if I need the slope at negative 3? I could plug it into here and I'd get negative 27. This is the power of the derivative. Now there is an alternative form to the derivative at a point. So if you want to find the derivative of f at a single point, you can actually do it as this difference quotient. It's called a difference quotient because you're doing the difference or subtraction, and it's a quotient because it's being divided. So you can actually use this form. And what example 2 illustrates is that when you do this form right here, your setup is a little different. You'll have an a value, and so when you do all the algebraic solving and you take your limit at the end, you're going to plug a in for x. So the answer you get here is your derivative at an a value at a point. But what you would essentially do in the end, you would then actually just plug in an x for the a spot, and now you have your derivative formula.